Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and in this video we are going to solve another gate question. This question was asked in the year 2017 for 2 marks. And this question is related to preemptive scheduling algorithm, right? So let us read this question. So the question goes something like this. Consider the set of processes with arrival time in milliseconds, right? CPU burst time again in milliseconds, and priority where 0 is the highest priority shown below. So as you can see, we have a bunch of processes P1 till P5, right? We have 5 different processes. And in this table, the arrival time, the burst time, all of these, which are in milliseconds, have been listed. And the priorities associated with each process is also shown, right? Here, 0 is the highest priority. And like as we increase the number, the priority decreases. So 0 is the highest priority, then 1, then 2, then 3, and fourth, that is process P5 is the least priority, right? This is what priority means. So by priority we mean that when we are deciding that to which process should the CPU be assigned, then we will be considering the priority. Processes with higher priority will be given preference, whereas with the processes which are lower priority, they will be pushed backwards, right? So this is the data, right? So let us summarize what we have. We have a bunch of 5 processes. This is the arrival time, burst time, the priority, right? So this is the first crucial piece of information. Then the next statement in the question is that none of the processes have IO burst time. This means that all of these processes, they're only executing on the CPU. They will not be using the IO devices. So this makes the scheduling much more simpler. We are only concerned with the usage of the CPU. So when IO bursts are there, then we have to kind of track the execution both on the CPU as well as IO, right? But here the question is simple. In that sense, it says that none of the processes have IO burst time. So no IO burst time, right? And the final statement is that the average waiting time in milliseconds of all the processes using preemptive priority scheduling algorithm is dash, right? So the question is basically saying that given this information, what is the average waiting time? So if you look at the time that is spent by a process in a given system, then there are two types of times. Basically, one is the burst time and one is the waiting time. Either the process will be executing on the CPU and that portion of time is considered as burst time, or the other part is that if it is not executing on the CPU, then it will be either waiting for the CPU or it might be blocked, right? So that is the waiting time. But since we are not even concerned about IO devices, let's just say that when the process is not executing on the CPU, it is ready. It's just that it is waiting for the CPU, and that is what the waiting time constitutes of. So there are two main parts of the overall life of a process. One is the burst time where it is executing on the CPU. The other is the waiting time where it is waiting for the CPU to be assigned to it, right? Now the question is asking what is the average waiting time, right? So for all of these processes, we have to calculate the individual waiting times and find the average and then report the number in milliseconds. And the most important part is that the scheduling algorithm that we are going to use in this question, it is preemptive priority scheduling algorithm, right? So priority scheduling algorithm is basically whenever you have to take a decision, right, out of all the candidate processes that are there in the system and ready to execute, you pick the one with the highest priority, right? And preemptive, this is the preemptive version, which means that if there is a candidate which has a higher priority than the process which is currently executing on the CPU, then we have the liberty, the operating system has the full liberty to take the control of the CPU from the currently running process which has a low priority than some other candidate, right? So the control of the CPU will be taken away from the currently executing process and be assigned to a process which has the highest priority at this moment of time. So this is what the preemptive means. That is, we can basically, the operating system can take control of the CPU from a running process to assign to it to another process which has a higher priority, right? So this is the last piece of information, that is, we are going to use preemptive priority scheduling, and what we have to find is that the average waiting time and then report it in milliseconds, right? So this is all of the important pieces of information. Now let's solve this question. So let us now make the Gantt chart, and from the Gantt chart, we'll get the completion time for all the process. We'll get the overall schedule, right? And from the completion time, then we can get the waiting time, right? So we are going to use preemptive priority scheduling algorithm as we discussed, right? So these are the 5 processes. We have the priority with each process, arrival time and burst times, right? So at t is equals to 0, you can see at t is equals to 0, process P1 arrives and it has a burst time of 11 milliseconds. So now let us start the execution. So process P1 has arrived, right? It is time instant t is equals to 0, and we have not yet scheduled the process on the CPU. It is waiting to be scheduled. Now if you see at t is equals to 0, there is only one process in the system, that is process P1. All the other processes will arrive at a later point in time, right? At the earliest, process P4 will come at time instant 2, then the other processes will arrive. So from 0 till 2, there is only one process in the system. Whichever algorithm you use, there is only one choice, that is process P1 will get to execute at least from time instant 0 to time instant 2. There is no question about priority in this case. It's the only process, right? So we will schedule process P1 to run for 2 milliseconds, right? You can see now the remaining burst time has reduced from 11 to 9. It executed for 2 milliseconds. What happens at t is equals to 2? At t is equals to 2, you can see process P4 has arrived, right? It has arrived at t is equals to 2. It has a priority of 1 and it will execute. Basically, the burst time for process P4 is 10 milliseconds. Now see this situation. There are two processes in the system, P1 and P4, and now we have to make a choice. Till now, only process P1 was there, so there was no choice. Now since there are two processes, we have to make a choice. And on what basis shall we make this choice? Basically, the operating system will consider the priorities. So process P1 has a priority of 2 and process P4 has a priority of 1. So in this case, in this scheme, the lower the number, the higher the priority, right? The priority is basically is inversely proportional to the number. So 0 will have the highest priority, then 1, then 2. So we can see that process P4 in this case has a higher priority since it has a lower priority number, right? So process P4 will be now allocated the CPU. And till what time instant it will be allowed to execute? Until a new process comes into the system. Until a new process comes into the system, till that point we are sure that there are only two processes, and out of all these two processes, that is P1 and P4, the higher priority process is P4 and that is what is executing. So as you can see, the next arrival is at t is equals to 5. So from t is equals to 2 to t is equals to 5, that is for 3 milliseconds, we can definitely be sure and give the control of the CPU to process P4. During this time, it is the highest priority process, right? So you can see how preemption is working. Process P1 was preempted and the control of the CPU was given to process P4. You can see process P1 has a burst time which is quite long, right? It has a burst time of 11, but it got preempted. That is, the control of the CPU was taken away from process P1 and given to another higher priority process, that is P4. So there are two things that you have to see: what is the priority, and you also have to take care of the preemption, right? So process P1 was preempted and process P4 was now, it gets to execute up till at least t is equals to 5. From t is equals to 2 till t is equals to 5, it will get to execute for 3 milliseconds, right? So this is process P4, right? You can see the burst time has now reduced from 10 to 7, right? This is now the remaining burst time. At t is equals to 5, process P2 comes into the system. It has the highest priority, right? You can see it is priority 0. It is P0. So it is the highest priority process that is ever going to arrive in the system, and it has a burst time of 28. So since we know that process P2 has a priority of 0 and 0 is the highest priority, we don't need to think any further. Out of all the processes that are there in the system, P1, P4 and P2, P2 has the highest priority. You can see 0. So this is the optimal candidate to give the control of the CPU, right? So we can see again there is a preemption. We are preempting a lower priority process in favor of another process which has a higher priority. In this case, P4 is being preempted, which has a lower priority, that is 1, and we are allowing the process P2, which has a higher priority of 0, to run. And we don't need to think now up till process P2 completes. Process P2 has a burst time of 28. Whichever process arrives in between, it will wait because P2 has the highest priority. So for 28 milliseconds, we do not need to do anything. So process P2 executes from time instant 5 till time instant 33. 5 plus 28, that is 33. And you can see process P2 is now done. We are now at time instant t is equals to 33. And in the meanwhile, all the processes have arrived, because you can see process P3 has an arrival time of 12 and process P5 has an arrival time of 9, both of which are less than 33. So by time instant 33, all the processes that were yet to arrive have now arrived. So apart from P2, all the other processes are now remaining. Now, since all the processes have arrived, we have a clear picture. We have a global data, right? there would be no need for preemption now, because since all the processes have arrived, we can just schedule the CPU in the decreasing order of priority. So all the four processes that are now left, and they are the only processes that will there be in the system till the end. So these four processes, we can allocate the CPU to them in the decreasing order of priority, and there will be no further preemptions. Why will there be no further preemptions? Because in order to have a preemption, there must be some new process, some new input, right? But since we already know the data, we already know the processes that are going to execute, this now reduces to a non-preemptive version. I mean, it's still we are still following the preemptive scheduling policy. It's not that the policy changes, but now it behaves like a non-preemptive policy because all the processes are there. We have the data for all the process, and we will be scheduling in an optimal manner. Preemption is required when we schedule a process, but later on a better candidate was available. But now, since we already know the information about all the process, the order in which we will schedule will be always optimal, right? Preemption happens when some new candidate comes and the optimal candidate changes. That change won't happen. So let's see what are the remaining processes: P1, P3, P4, P5. So process P2 is done. It had a priority of 0. So we'll next consider the process P4, which has the next higher priority, right? So P4 with a priority of 1 will go next. It has a burst time that is remaining of 7. So from time instant 33 to time instant, okay, I did not show this. So we can see that process P3 and P5 have also arrived. We already discussed this, right? P3 and P5 already arrived before time instant 33. Now P1, P4, P3 and P5, these are the remaining processes that need to execute, and we are just going to schedule them in decreasing order of priority. So process P4 executes from 33 till 40. You can see it is now finished. Now P2 and P4 are done. Remaining is P1, P3 and P5. So after priority of 1, the next higher priority or the next optimal candidate is the process with a priority that is 2. It has a burst time which is remaining 9. So from 40 till 49, we can allow process P1 to execute. You can see till time instant 49, P1 executes, and now it is done. Now we have only two processes remaining. After priority 2, we will now schedule the process with the next higher priority, that is priority 3. It has a remaining burst time of 2. So from 49 till 51, this executes. So completion time of process P3 is 51. Now the last process, the least priority process, which is process P5, now it gets to execute. The remaining burst time is 16, right? And you can see it finishes by time instant t is equals to 67. So the lower priority processes have to wait, right? This is the fundamental idea, that whenever there is a process which has a higher priority, even if there is a process with a lower priority running, it will be preempted. The best candidate, the one with the highest priority, will be allowed to execute, right? And at one point in time, basically when all the processes are already there, then we don't even need to do preemption. We just schedule the processes in decreasing order of priority. That is what we saw in this example. So now we have the completion times. Let's do the further calculation. So in order to get the waiting time, first of all, we need turnaround time, right? So turnaround time is completion time minus arrival time. So why do we need turnaround time? So as I said, so basically a process spends a certain duration in the computer, right? There is an arrival time and there is a completion time. So from arrival time till completion time is the entire duration that the process has spent in the system. So this entire duration is known as the turnaround time. So turnaround time is basically a generic term that we use in daily life also, which signifies the total time that it takes to complete something, right? So from the time instant the process arrives into the system till the time it finishes, that total duration that it spends in the system is the turnaround time. And in this turnaround time, there will be two things that the process will be doing. Either it will be executing on the CPU, and that part when it is executing in the CPU is counted as burst time, or it would be waiting for the CPU to be allocated to it. So that part won't be included in burst time, that will be in the waiting time. In this question, we are interested in the waiting time. That is the time during which the process is waiting for the CPU to be assigned, not executing on the CPU, right? That is burst time. So to get the waiting time, we simply have to subtract the burst time from the turnaround time. So basically from the total time that the process spends in the system, if you subtract the time it has spent on execution, then you get the time which was during which it was not executing, right? So that is how we calculate the waiting time. So now, since we have the waiting time for all the processes, we can take the average, and the average waiting time comes out to be 29 milliseconds. So we have to report the answer in milliseconds. So this is the solution to this question. That is, the average waiting time is 29 milliseconds when we use a preemptive priority scheduling algorithm for this set of processes, right? So guys, this is the solution. This was it for this video. Thank you very much for watching. I'll see you in the next video. Thank you.